Another unit in our pre-AP chemistry adventure here. And this unit is actually 2 units in one. We are kind of running out of time at the end of the school year, so there's actually 3 units that we should have done, but we took 2 of them, we condensed them together. So we're going to look at acids and bases in this unit, and then we're also going to look at reaction rates at the very end. Both of these things are very important to your journey going forward into AP Chemistry, so we wanted to make sure that you got the basics of both acids and bases and reaction rates. So the first thing that we're going to look at is your acids and bases. And as we look at those acids and bases, we're actually going to do a video here. And this video is Tim and Moby, you might remember it from middle school. And they're going to explain just some basics first of acids and bases. We're going to do a review of naming, we're going to predict some products, and we're going to look at what is an acid and what is a base and what are their characteristics. So we're going to start today with the video first.
Stings. Dear Tim and Moby, we're learning about pH, and I need to know how acids and bases are different. From Chelsea. Well, lemon juice is certainly an acid. It tastes sour, and it stings if it gets in your eye or a cut. Substances like vinegar and some soft drinks are acids too. Acids release positively charged hydrogen atoms when they're dissolved in water. When those hydrogen atoms combine with water molecules, hydronium ions form. Acid solutions can conduct electricity since they contain these ions. Some acids can even eat away at metal. And those cool stalactites and stalagmites in caves are formed by carbonic acid dissolving the minerals in the rock. A sour taste is a property of acidic solutions, but you don't want to go around doing acid taste tests, because that's dangerous. The pH scale gives you a measure for identifying acids and bases. pH stands for potential of hydrogen, and the scale ranges from 0 to 14. A pH of 0 means extremely acidic, and a pH of 14 means extremely basic. Anything with a pH of lower than 7 is acidic, and anything with a pH of higher than 7 is basic. A substance with a pH of exactly 7, like distilled water, is called pH neutral. Right, I'm getting to the bases. Bases also contain hydrogen, but they form hydroxide ions when they dissolve in water. Since bases contain ions, they can conduct electricity, just like acids. Chalk is a base, and so is soap and other cleaning products. Basic solutions feel slippery and taste bitter. But again, you'll have to take our word for that, because it's never a good idea to go around tasting stuff, especially in a science lab. Hydroxide ions don't react with metal, so a base won't damage your pots and pans like an acid could. Hey, thanks for doing those dishes, but you might want to slow down. You didn't get me that time. Safety goggles.
Okay, so looking at that video, it looked at the properties of your acids and bases. We're going to get more into depth in that as we go through the unit, but today what we're going to do is we're actually going to work on just naming an acid and naming a base. It's been a little while since we've done that, so we're going to go back and we're going to look at the rules again, because you're going to see a lot of these acids and bases, and you'll need to be able to write the formula and write the name of those compounds. So the first ones are technically called binary acids. I just call them IDE acids. And this means that you have hydrogen. Hydrogen's always written first because it's a hydrogen ion, so hydrogen with a +1 charge. And it's paired up with an anion, that negative charge that ends in IDE. So if you have your periodic table and you have something like fluorine, fluorine turns to fluoride. Chlorine is chloride. Bromine is bromide. Oxygen is oxide. So as an anion, they end the actual compound, or not the compound, the element with IDE to show that it has a negative charge. So looking at this, you're going to have hydrogen with fluoride, or hydrogen with sulfide, or hydrogen with cyanide is a polyatomic ion. So if you remember on the back of your periodic table, you have a list of polyatomic ions. Anything that ends in IDE, which is cyanide and hydroxide, is going to get your IDE as well. So with these, in order to name them, this is where you put hydro at the beginning of the element. The hydro means that water needs to be present in order for it to break down. So it doesn't mean hydrogen, it means water in this case. So we have hydro at the beginning, and then you take that like fluorine or chlorine or whatever, and instead of putting IDE at the end of it, you put ic. So take away the IDE, put in ic instead, and then you write acid. So on these, they're going to start with hydro, you have something there, and then you end it with ic instead of IDE. All of these are acids, so they're all going to have acid in that second spot. Now there are some weird ones. If you have hydrogen with carbon, it doesn't actually say, like, it doesn't really follow the rules, what I'm trying to stumble through. So if you have carbide, that would be your carbon with that -4 charge, but it would actually, when you change it, you put the ON in the middle of it to make it sound better. So it's hydrocarbonic acid instead of hydrocarbic. I don't count off if you name it wrong, like if you leave out the ON, but I will always write them correctly. Same thing with phosphorus. You would have hydrophosphoric acid. The OR is there to make it sound better. And then instead of hydrosulfic, it's hydrosulfuric. Again, as long as you follow the rules, I'm okay. But when you are reading them, I'm going to write them correctly. So these examples I'm going to come back to when we're done with all of the rules on all of your naming. So we're going to look at polyatomic acids next. And with your polyatomic acids, these are the ones that end in ITE, not IDE, ITE, and ATE. All of these are on the back of your periodic table on your polyatomic ion sheet. All of them are going to end in ITE or ATE. There are other polyatomic ions like ammonium. You won't ever find that in an acid. You have hydroxide, which we already talked about. Cyanide, we already talked about. But these, your ITE and ATE, are going to follow these rules that they do not get hydro. So with these, you're going to take away the ATE. And when you take away the ATE, you put IC instead. And then you have ITE. On those, you're going to take away the ITE and put OUS instead. And then again, they're going to end with acid. So again, they don't get hydro. Don't get hydro. They have an oxygen present, so they don't get hydro. So take away ATE, put ic, ite becomes us. So with your polyatomic ions, you do have your polyatomic ion chart that you're going to need when we're doing our assignments. You have your 12 polyatomic ions that we had to memorize. Those were never given to you in a normal year. Last year, or this year, with 2020 school year, the 2021 school year, they didn't have the polyatomic ions. But you normally have the 12 polyatomic ions that you have to memorize. Those were never given to you. All of those are 8s. Well, most of them are 8s, I guess I should say. So with your weird ones on these, again, phosphorus and sulfur, they're going to cause a little bit of a problem. In order for them to sound better, they put the UR or the OR in them. So instead of sulfic, it's sulfuric. Instead of sulfurous, I can't even say that without sulfus, you would have sulfurous. And then same thing with phosphorus, it's phosphoric, and then phosphorus. So with your names, I won't count off as long as you just follow the rules, but I will always write them correctly. So again, I'm going to come back to these examples when we do the base naming, and then we'll be all done. So a way to remember them, I had a student that taught me this years ago, and it kind of stuck with me. It said that I ate the acid, it was ick. So I ate the acid, ate becomes ick, it was ick. Don't bite us. ITE is OUS. Neither of those have hydro. So ate is ick, ite is us. So with your bases, these are just ionic compounds for the most part. There's one that's not. But with your bases, when we go to name them, you're typically going to see hydroxide and carbonate and bicarbonate. So when we have hydroxide carbonate and bicarbonate in those compounds, you just name them like you would any other compound. So if you have sodium with hydroxide, it's called sodium hydroxide. Your first element name stays the same. Second one is going to end with your polyatomic ion or IDE. If you have a transition metal, those get Roman numerals. So looking at your bases, you're going to see compounds with hydroxide, carbonate, bicarbonate. And then there's one that you just have to know. The one that you have to know, the NH3, that's called ammonia. Now ammonium is NH4 plus 1. It's on your polyatomic ion sheet. Ammonia is NH3, and it's just something that's usually called that. Instead of saying nitrogen trihydride, you actually just call it ammonia. And from here on out, you can just call it ammonia. Just like water is H2O, we don't usually call it dihydrogen monoxide, we just call it water. So ammonia is the same way. So we have some examples that we're going to do. Sorry, I'm flipping through. I thought I had one more slide. So I'm going to go to my document camera in order to do these examples. And when I'm looking at my examples here, they're actually from the notes, but we have HF. When we have this, we kind of have to look to see what is going on here. This H means acid. So with that H meaning acid, that just means that I'm going to have hydrogen ions present. So we're going to end the word with acid. Then I have my F part of it. This F, when it's in a compound, is called fluoride. That ends in IDE. So when we are naming this one, if we have hydroic, that is ide, just ic is 8, and OUS is ite. So this one is fluoride, IDE. So this is going to start with hydro. Instead of fluoride, I'm putting fluoric. And then I write the word acid. So the acid comes second in the name, but it's the hydrogen there. So because it's ide, it's hydroic. The next one, hydronitric acid. Hydro means that this used to be IDE. Acid means that hydrogen ions are present. So we're going to take hydrogen that has a +1 charge, and we're going to pair it up with nitride. Nitride, on our periodic table, is nitrogen. Nitrogen has a -3 charge. So we have N with a -3. When you have your plus and your minus, those disappear, and then we swap and drop. H3N is your formula there. So hydronitric acid, H3N. The next one, HC2H3O2. Everything after the H is going to be a polyatomic ion. So I'm going to look for a C2H3O2 on my chart, or it's just one that we have to memorize. But C2H3O2 is called acetate. This ends in ATE. So looking at our rules up here, if it ends in ATE, we take that away and we make it IC. So this is called acetic acid. Because again, that H just means that it's an acid. The next one, carbonic acid. This ic means that it used to be 8. There's no hydro at the beginning. If it was hydro, it would have been ide. But because there's no hydro, ic is 8. Acid means that hydrogen ions are present. So with this one, we're going to take hydrogen, it has a +1 charge, and we're going to pair it up with carbonate. So when we look at our chart here, we find carbonate, again, it's one we had to memorize, or we look it up and it's CO3 - 2. So we're going to pair up hydrogen with CO3 - 2. The plus and the minus disappear. The 1 comes over here, the 2 goes over here, so you have H2CO3. Now these two are both bases. I know that they're bases because this has hydroxide. Hydrogen is not in the first spot. And then this one doesn't say the word acid. So with this one, we just go back to our regular naming rules. We have Mg, that is magnesium. And then OH is called hydroxide. So when I look at my periodic table, Mg is here. It has a +2 charge always, so it doesn't get Roman numerals. So I have a metal, no Roman numerals. The Roman numerals, remember, only in this section, and tin and lead. So we have Mg, magnesium, nothing special that you need to do there. And then OH is hydroxide. So this is just called magnesium hydroxide. The next one, calcium bicarbonate. So I have to get my periodic table here because I need the charges. Calcium is right here. Calcium, number 20 down here, has a +2 charge. Bicarbonate, let me flip over my chart. Bicarbonate, when you find it, it's right here. It is HCO3 -1. So I'm going to swap and drop. So we have Ca, open parentheses because it's a polyatomic ion, and polyatomic ions go in parentheses. HCO3. The 2 travels over here. The 1 travels over here. So it's Ca and then HCO3 2. Just to show you an example of one that has Roman numerals, just to refresh your memory. Let's say that we have, let's see if I can make this up on the fly. NiOH3. Now I already told you that it's going to have Roman numerals, but Ni is nickel. Nickel on the periodic table is right here. Nickel is going to get Roman numerals because it is in a state that we don't know the oxidation number. So we're going to get Roman numerals there, and then OH is hydroxide. To figure out what goes in the Roman numerals there in the parentheses, you can do this one of 2 ways. I've got 1 nickel, and I've got 3 hydroxides. I know that each hydroxide has a -1 charge. In order to equal 0, that means nickel has to be 3 in order to equal 0. Or you could try to reverse swap and drop where that 3 comes over here, the 1 goes over here, but you have to make sure that this charge is all correct. So in this case, we got the same answer, nickel 3 hydroxide. If you notice there are no covalent compounds, you won't have to worry about any of the prefixes. It'll either be a transition metal or not. Other than that, I hope you guys have any questions you ask. Otherwise, have a great day.